So I would like to start with something. 1995 was a very, very special year for mathematicians. There was a mathematician celebrity, Andrew Wiles. He managed to solve a problem that was standing for 358 years, the Fermat last theorem, which was a conjecture up to the point it became a theorem. That's my opinion about it. Although Fermat himself was a genius of numbers, although, by the way, was an amateur mathematician, apparently because he had a proper job. Not that mathematics is not a proper job, but he had a job, he was in court. So it was a marvelous time for a mathematician. He took the headlines. Beside the prestige, the money, and everything else that came with it. Mathematical immortality. I would like to speak with Professor Misha a bit about Fermat last theorem. Please, Misha.
Well, the first, what's very, very interesting is that I'm slightly objecting to the name last theorem. In some other languages, it's called actually Great Theorem of Fermat.
Okay.
Because in fact, it wasn't the last theorem. It was claimed that he wrote, they formulated it.
Yes, on the side of
on the
book.
side of the Diophantus
Yeah.
arithmetical book in 1637.
Which is, yes, exactly. And it took a few decades after, he still, yes.
And I think only in 1670, when his son already after passing of Fermat was publishing things, he discovered it and he published it. So it was published later than the other of his kind of mathematical and other things, but it was not the last. But it was great. In comparison, the small theorem of Fermat was written 3 years
That's
later.
about prime numbers?
Yes.
Oh, yeah.
Was written 3 years. Was written 3 years later.
Which Euler managed to find a problem with, right?
Yes. Yes.
Euler
yes.
always finds the problems or he finds the solutions.
Yes, and the interesting thing with this theorem of Fermat, probably we can step back. You mentioned that he was an amateur. He wasn't a professional mathematics.
But a great amateur, though. Oh my God.
Yes, but first one need kind of to say few very good words about the French school of mathematics,
Please.
which was extremely, in a way, 17th century was from mathematics points of view, as well as from many other points of view, the French century. It's still called golden century, I believe, in French history. But before that, before 17th century, in Europe at least, the first violin, so to say, were played by Italian mathematicians from Fibonacci time, etc., etc.
Okay.
But in the 17th century, the French took over, and we all know about Pascal and Descartes.
Mersenne
Yes.
was a focal point for many mathematicians.
And also the Academy of French Sciences, which was founded at that time, a lot of mathematicians made to it. So mathematics became suddenly extremely popular. Popular subject. It was popular with the state, popular with the church, popular with the king. So it was kind of everybody from aristocracy to the proletarians, everybody were interested.
It was a good hobby, mathematics. Good.
Yes,
We
yes,
should,
yes.
yeah,
And
should
it
go
was-
back to it.
It was started also kind of because people, all the chattering classes, all the kind of educated classes and rich classes, they were gambling and playing cards. Then the mathematics
They
became
needed,
the
yes. And Fermat was part of it, right? He started dealing with probability. I believe that he put the foundations for it in Pascal, maybe. I'm not sure about it.
Yes, so this especially was probably developed slightly later in 17th century when they already kind of were based on the non-French mathematicians, on the Leibniz and Newton. But that was probably already later in the 17th century. That's one very interesting point. The second very interesting point is, for me, kind of even how he come up with his theorem. The continuity of mathematics.
Beautiful.
Beautiful.
All the way back to Pythagoras.
All
And
the way
then
back to
to-
Pythagoras. Because of Diophantus, he
Yes.
was writing on the margin of the Latin translation of Greek Arithmetica of the Diophantus's book. Diophantus was, in a way, probably I personally would say, not as famous as many other mathematicians, as Pythagoras, as Archimedes, as Euclid, as many of them. For some reason, Diophantus is not as such as household name, and wrongly so, because he really on the 3rd century of Common Era he took all the knowledge of preceding 7-8 centuries of the Greek mathematics and kind of unified it.
Can you call him the father of algebra? Because Khwarizmi, Muhammad ibn Musa al-Khwarizmi, which I believe 400 years after, he is the one who actually, yes, okay. So he is the one who actually came up with the, yeah, you're right, a bit more. He came up with the concept of algebra, but can you say Diophantus maybe was the first?
Diophantus was one of the first, probably the first person, but maybe, who knows, maybe because he lived already in the time of the late antiquity, just before the Roman Empire and its Greek part became Christian. And for some reason, I don't know why, would be interesting to research, there was certain tension between the triumphant Christianity of that time and the sciences, because maybe sciences had a very much of this pagan flavor of it, maybe because it was around all this kind of academia, philosophical academia, so from the kind of nascent of Christianity, which is in a way a bit strange because Bible is quite mathematical. From the nascent Christianity, young Christianity, triumphant Christianity, the science felt a little bit on opposition of that. So it is not kind of completely surprising that the center of gravity very soon, from the 4th, 5th century, went away from Byzantium, from the Greek part of the Roman Empire, into places like India first, China to an extent, but also the Muslim lands, like you mentioned, like Al-Khwarizmi. So maybe they didn't have time in a way to fully internalize the algebraic part, but yes, absolutely, he was algebra. You can call him the father of algebra.
You can. Now, okay, so Fermat, centuries after, reading Arithmetica and comes up with this brilliant idea. He comes up with this incredibly brave, maybe prophetic conjecture, which we know as Fermat's last theorem, or the great theorem, as you called it. Can you explain a bit about it? Before you do, actually, I just want to say something. Number theory, for me, is amazing. It's one of, I think, probably the most favorite branch of mathematics, the one that I would really love to understand. It's very easy, I think, to explain to people conjectures in number theory, extremely difficult as this theorem proved, to prove them. Because I think in other branches of mathematics, it's a bit more complicated to explain the conjecture. Here it's fairly easy, but to prove it, we needed many centuries. So please.
Yes, well, you kind of mentioned a couple of things. So let's kind of start for your second question about the simplicity. So, the simplicity of last or great theorem of Fermat is unbelievable because we have like three things, A, B, and C.
Yes.
We have A in the power of n plus B in the power of n equals C in the power of n, which n being a natural number and n is bigger than 2. We know, and I was kind of thinking about how kind of trying to explain these things more to make it more visual, to make it more kind of palpable.
Please.
And I came up with the things. The first, if we take Fermat, this formula for the n equals 2, which it doesn't consider, it reminds us our very own and beloved Pythagoras.
Pythagoras, yeah, of course. The 3, 4, 5, for example. Many people talk about it without even knowing what Pythagoras is.
3, 4, 5. So 3, what you I think alluding to is 3 squared plus 4 squared equals 5 squared, which is very, very beautiful. And actually thinking about it and kind of trying to meditate a bit in it, because I think mathematics is not only something which you think, something you live in, which you dive in, but you kind of meditating. So I was meditating.
I agree with you. Absolutely.
Which was in a way, we just probably in the last couple of centuries we started, even not in a couple of centuries, I would imagine great people like Einstein, of course, physicist, but
he meditated a lot.
He
was a genius of thought experiments. He actually had a great focus.
So I meditated a lot, not a lot, but meditated somewhat about it, and I just decided kind of to forget a little bit about what Fermat said and a little bit generalize it, not how Euler generalized it, which is probably the subject for the next time, but just take it for the any n being 0, n being 1, n being 2. So for n being 0, because any obviously number in 0 is 1, it doesn't hold, it never holds. Because a in the power of 0 is 1, b in the power of 0 is 1.
1 plus 1
equals 1. So it's obviously not true.
Okay.
Then we go into
n equals 1.
N equals 1, which is in a way quite obvious, quite trivial, because it would be a plus b equals c. For any a and b, you can find c, however big or small they are, so there's no problem. When we go into the n squared, then this is our Pythagoras theorem, and I wanted to kind of to think about a little bit more interestingly. I never read it, but I decided to experiment. And the very, very interesting thing is that, for example, whatever number a is, you give me any number, whatever it is, I can find number b and number c, so a squared plus b squared equal to c squared.
Fantastic.
And I can prove it, and it's very easy. It could be even number, it could be, it's very, very easy. In fact, when I was a schoolboy, I like these things. So for example, things like 12 squared plus 5 squared equals 13 squared. 144 plus 25 is 169. And I like to think what number. And actually, probably that time I came up with this theorem, which I just told you. I'm sure I wasn't the first one. It's not particularly
complicated. It's very nice. You know, they said that Albert Einstein actually managed to figure out some Euclid when he was young.
Yes.
Before, even without reading it. Anyway,
I was 10 or 11. I don't know how, maybe even younger.
So I believe you, Misha. That's why you're here.
I love the square numbers. So basically, for n equal 1 is completely trivial. For equal 2, it's also kind of, in a way, it needs a little bit of thinking, but you can place infinite number of these pairs, of these triples, of a, b, and c, which it holds. So kind of from the thinking of continuity, and I love continuity, I'm kind of probably a little bit more continuous mathematician, right?
Mathematician, or induction.
Yes. You would say induction, exactly. You would say, okay, forget 0. 0 is kind of a strange case. 1 is infinite amount of solutions. 2 is infinite amount of solutions. 3 probably would be infinite solution, or probably would be very big amount of solutions. But not completely not.
Yes, and that's the brilliant thing about it. And Fermat coming up with that bold statement. And he said, I proved it, but there is no evidence.
And not for 3, and not for 4, and not for 5, and not for anything.
Exactly, to infinity.
Okay, then what I'm trying to do, if, for example, I ask myself, if we can visualize through Pythagoras theorem, we can visualize the a squared plus b squared equals c squared, how can we visualize the, say, a cube, at least a cube, starting with cube, with three-dimensional things, a cube plus b cube plus c cube. And when I thought about it, the closest thing I got, and I will think about more, and probably would be interesting to look at the geometry of the cube, but looking at this thing, so for example, this 3, 4, and 5 which you said, imagine that I have nine balls, and I put them 3 by 3 by 3 together, or 9 cubes, or whatever it is. And I take 16 cubes, and I put 4 and 4 and 4 and 4. So now I can put them together and put something 5, 5, 5, and 5. So I can make from 2 squares with all these small cubes or squares or whatever, or spheres, I can make 5. And again, whatever number, according to my theorem, whatever number you would give me, I can find another C, B and C, where I can make these cubes, these kind of squares. Now I'm taking cubes, so I'm taking like building blocks, and I have, for example, the cube. I have like 3 by 3 by 3 cube, which is 27, of course. So I'm thinking, what kind of other cube I can construct? So together, I would get the third bigger cube. And apparently none. Neither for 3, neither for 4, neither for billion, nor for four-dimensional, nor 100-dimensional, nothing. Why? Completely counterintuitive. No, completely counterintuitive. And then what you're alluding, that's one question. The other thing what you're alluding, how on earth somebody who was even not a mathematician by education, somebody who was a lawyer, who had his duties of being a lawyer, his duty as a husband, his duty as a son, his duties as a father, as a citizen, as whatever, in the time when many people died from cholera or Black Death or whatever, how sitting and reading a Latin translation of the Greek mathematician, whatever, 14th centuries after that, he could write something which nobody could prove for 3.5 centuries.
And he said that he proved it. Even though that's another thing, because if he managed to prove it, there is no evidence for that. But if he managed to prove it, so he managed to prove something that was needed almost 360 years of mathematics, evolution of mathematics, of the language of mathematics to prove. That's remarkable. If it really happened, if we have to believe him. If he hasn't proved it and just taught it by intuition, by feeling it, by knowing it, that's remarkable. That's mathematical prophecy. Tell me, please.
Okay, we probably never know, because yes, indeed, when he wrote these things, as well as with a small theorem, he said I proved it, but he said, I think in both cases, he said it's too difficult
to put in the mind.
To put in a small
exactly.
way.
He said there is no space.
No space. In a way, I would probably kind of understand that, because the gentleman who proved in 1995
exactly,
took 240 pages. And you know what it is? All the notations now much more convenient. All the apparatus, all the kind of notations which we as a humanity developed in the last, whatever, 3.5 centuries, make our calculations much easier. So if it took, in the 1995, it took 140 pages.
I wonder how many it would have taken Fermat.
We can joke about
it.
Of
course. This is ridiculous. Yeah.
With the kind of how the English people would say about French, he was a Frenchman, he liked to boast.
Yeah.
I would imagine so that he was a very serious mathematician, and I would imagine that it wasn't just an empty boast. I don't think he would just lie.
I don't think, by the way,
I don't think so, because all my knowledge of mathematicians, scientists, all kinds of people of great intellect, they don't like to say bad things, to say stupid things, because they would probably err on the other way. They would say, I don't know, Socrates, I know it, I know nothing. They would be very very scientifically humble, very scientifically prudent and cautious.
Yes, I've seen it before. I think that Gregory Perelman, by the way, it was said the same about him. He's a very unusual character. He doesn't give interviews, but his colleagues said that once he managed to put the Poincare conjecture, the only millennium problem that was solved. Probably Fermat would have been a millennium problem, the most prestigious of them all, if it was not
Absolutely.
to be. Yeah, and probably more prestigious than the Riemann hypothesis.
He just missed it by 5 years. Yes.
but just one thing, it is amazing that he actually missed by proving it before. Yeah, it's brilliant. Yeah.
My kind of, I think when people say that I'm kind of channeling myself, thank God, and I just like my kind of feeling trying to tune in into him, that he did prove it. What can be that the proof didn't cover all the cases,
but enough for him to be confident to come with a statement.
It might have been done for number 3, for the power of 3, not for power of infinity. It might be also, which does happen, and which happened with a lot of even Fermat theorems, as you will be aware. Sometimes very, very great mathematicians were proving something, and then some other great mathematicians, sometimes even not as great mathematicians, would find certain inconsistency or mistake. So it would be extremely valuable. I think many people would give all their money or would work very hard for the opportunity to see what was the proof of Fermat's was. My feeling it was either for some sub-case, or maybe now with a magnifying glass, if we look at it, we would see something maybe inconsistency, whatever, which does not make him less great, as we will hopefully speak next time about the conjecture of Euler, which was disproven in 1966. What counterexample was found. Does it put in my mind, in your mind, anybody?
No, of course not.
Of course not for a second.
But Misha, I just want to tell you, I want to come back and actually speak about it because I'm fascinated by your opinion about it. You brought a brilliant subject last time, Pi, in the Book of Kings. Michael Atiyah, which I mentioned, the great mathematician, not alive anymore, unfortunately, a great speaker as well, a great advocate and promoter of mathematics. He spoke a lot about feeling. He spoke about the taste for mathematics. You know what it means. It's an artistry. Now, Euler, I read about the Basel problem and I'm studying it, and it's fascinating to me what an artist Euler was. Besides the fact that he knew everything about mathematics that you could have known at that stage in time. Plus, he was a great mind of mathematics, extremely original, but also he took chances. The Basel problem, he mixed so many different fields of mathematics, and his proof, the original proof, when he came to the pi to the power of 2 divided by 6, was not even a good proof yet. But he knew where he's heading. It's unbelievable. He took chances. He's like an explorer. He's like one of these men on the sea going and trying for a newfound land. It's unbelievable. How much of it do you really see in mathematics? Because the problem today is that, as we spoke about it, people think that mathematicians are almost like good computers, robots. They just go, oh yeah, this makes sense because of the procedure, follow procedure, follow procedure. No, there is a lot of intuition. You first see a vision, and then you are adding toward the vision.
Yes, you're absolutely right. So what I see with this kind of unbelievable ability of some people, and it's not so many of them, to prophesize in a way how it will be. It is a bit prophetic. I probably would compare it with, in my mind, with people like Mozart, because it is amazing that this person, and I'm very big fan of Mozart, as many musicians of his level, he heard the music in his ear. I want to say, mind, eye, whatever, mind, ear. He heard this music, and he was able to, in a way, to translate it into the musical notes. He was able to hear this melody and translate it into the trombones or violins or whatever. So into the song, into the voice of the person. So how can you do it? How is the person's mind, even if one was trained? It is a mystery. In a way, mystery like child prodigy. But generally speaking, anything in this way is a mystery. It's not, in a way, more mystery how we are come to this being, how from a mom's cell and that cell, which become one cell, we develop, all of us. When the nose is in front and the ears and the back, and God forbid, and that does happen some people are born with certain defects, but the most people, and even with the people who have some problems, the most of them is done because there is certain program. How is it possible? I don't know. How our consciousness comes being. The child comes to the life and suddenly he or she said, I like this, I don't like this. I like this music, I like this food, I want to be a musician, I don't want to be a painter. How it comes? Yes, a lot of influences, of course, but there is some mysterious spirit, I don't know what it is, which comes alive in each of us. In some more talented people, as talented people physically, for example, some people can bend better than others. Some people have immense ability to work, which others don't.
Yeah, some people can see. And mind you, these people, someone like Euler was not just a savant, no disrespect, but there are some people who can recite the digits of pi, I don't know, for 10,000 digits of pi by just knowing it. But he actually used his knowledge and ability in order to prove things, in order to find, to advance mathematics, to create, to add. This is the creative process is mind-blowing. Yeah.
Yes, it is prophetic because, by putting that we all miracles, and we are, there are certain people on our kind of average level, which are miracles. The people like whether Fermat, how he was able to see it so far. that's beyond our understanding. It's
Absolutely.
it's a very interesting way, and the question how the mind works. But definitely he's a person who needs to be celebrated and needs to be
And
acknowledged.
he definitely, I think that his theorem is one of the most famous simply because it was so unsolvable for so long. If we can actually dedicate few minutes, if it's possible now, just to explain. So it was solved. It was solved. I'm just going to say it like that in a nutshell because it's very complicated to explain it, and I'm still studying it as well, because of Taniyama Shimura. Two Japanese mathematicians, post-war mathematicians in Japan. It was very difficult situation back then. Not enough mathematics compared with Europe, and they had to start from scratch. Maybe that's what motivated them. Great friends as well. Unfortunately, one of them committed suicide later on. Terrible tragedy. And together they developed the conjecture Taniyama Shimura, which connected modular forms with elliptical curves. And Andrew Wiles, who was actually into elliptical, specializing in elliptical curves, but then very inspired by the idea of solving Fermat's last theorem since he was a kid, decided to go for it, and then he will prove indirectly Fermat's last theorem by the Taniyama Shimura conjecture. Can you explain a bit, slightly, just a bit about modular form and elliptical curves, the connection, and what was really going on there?
No, I think that would take a little bit more time because in
Fair
a way,
enough. No, it's complicated.
because of those two gentlemen, these things were proven. In a way, they created their language.
Mhm.
They create material which allowed Andrew Wiles to sort it out. So, and in a way, what they've done, and you're absolutely right, they kind of made a complete breakthrough in mathematics in the country which at that time was not as mathematically developed.
Mhm.
The profession probably was not as respected as in the good universities in the West, in the United States, but they made complete breakthrough on this thing. So it was completely great what they done.
Okay, we can maybe next time try to speak a bit about it. I think that it's easy to explain the conjecture, but again, coming back to the proof, I think that someone said as well that there are only very few mathematicians in the world that can actually go through the Andrew Wiles proof and understand it.
Yes, that's the situation that look, it's very long proof. I think it's 140 pages. So in order to prove it, and that's very interesting, that again extremely interesting things, and which probably worthwhile to devote at least half of the talk at some point.
We will.
That it has been very much with probably with the great theorem of Fermat more than anything else. But there were many other examples. As you said, very simple problem.
Mhm.
Looks completely very simple. You can explain to anybody who is 10 or 11 years old, maybe younger. It's not that it took 3.5 centuries to prove it. What happened in between? A lot of language was created.
Mhm. Yes.
It's almost how to say that. So, for example, in order to answer a very simple question in English, where is my book? Or something very simple. You need to learn 100 languages only to answer this question. It's completely, it's very counterintuitive again. You need to develop the subjects of mathematics in order to answer a simple question. So what happened over the centuries? Partly because of Fermat theorem, partly because of the need of the economy, of, I don't know, navigation, of space, of military. Very often mathematics was developed, but very often in the case of Fermat, the human curiosity, because of beauty of this problem, encouraged people to develop new subjects, new areas. And this is, in a way, if we want to be practical about mathematics, so it's okay, who cares what Fermat said, and who cares the proof was. But if you want to look from a practical point of view, in the process of solving these things, proving it, huge mathematical apparatus was developed, which opens like absolutely unlimited, not exaggerating, unlimited opportunity for other mathematical areas to be developed. and practical applications.
That's a thing. I think let's just finish with a question like that, or actually a statement, maybe a question. I mean, you will probably interject. They said, I think they asked about someone asked about Fermat's theorem. I saw some sort of an interview with few mathematicians and then a journalist who is not a mathematician but he writes about the subject. I forgot the name, and they asked him, okay, so how can you use it? What is the point of it? You know, for the people who read in the paper, they read, okay, it's very impressive that this guy is probably got to, you know, they look at, oh, he's so smart, he's probably the smartest man in the world. I'm talking I'm taking it to the basics. But what can we do with that? That's a beauty. It's an art, like anything else. But you know, but I think that today, if you cannot translate things into technology or into money, it seems like they are useless.
You're absolutely right, and it's a little bit kind of, I would say, offensive and bad, because if you talk about the arts, well, if somebody comes, what's the point of Mozart? What's the point of opera? What's the point of Beatles? What's the point of this? Whatever you name your favorite music. If somebody would come to you or say, the person's, I'm sorry, the person's a moron. He or she doesn't understand you.
Right, I agree with you, it's a moron.
Exactly. Or for example, somebody, well, what's the point of Chagall or Picasso or whatever? If you don't understand, go next door and...
But this is the misconception, you see, Misha, because mathematicians are supposed to be practical people according to the general public. They are solving our problems so we can have a better iPhone.
That's exactly what I'm going to. When you go to beautiful things like, for example, chess, nobody said, oh, this... Well, Einstein said about Lasker, yes.
Yeah, waste of time and waste of talent.
Yes, he did. But generally speaking, majority, and look, Einstein can say that, but most of us can't.
Yeah, exactly.
But I love chess myself very much. And to say that what's the point of these things? You don't create it, you just take the pieces, you move the pieces, and you put it back in the box. What's the point? Of course, you have relaxation, you improve your brain power, you try to avoid dementia. It's all very, very great. But you can't only look at things with the utility. Sports, everything, almost everything is fine. But mathematics should work very hard and sweat in order to produce to us. I think it is understandable. It's just coming to me. Imagine you have two friends, and one friend always entertains you. So you wouldn't expect anything from him, right?
Yes.
And the other friends sometimes entertains you, and sometimes brings you a lot of goodies. Makes you rich, gives you a car, gives you a home, gives you whatever, electricity. I said, okay, don't entertain me. Let this guy who is a chess player or musician entertains. You bring me goodies. You bring me these things. The problem with these things, and it's very, very known, parables written about it. One of them, kind of a pig under the oak tree. If there is no pure mathematics, there is no applied mathematics.
Absolutely.
They kind of...
That's the thing, yeah.
I wouldn't personally, working a lot in applied mathematics myself, would not say that kind of pure mathematics is the goddess and the applied mathematics is servant. But they kind of left and right hand. We need to develop both of them. Otherwise, we will be very, very short-sighted. We would be very kind of asymmetrical.
You come with a concept like imaginary numbers. No one really knows what to do with that, and then suddenly, oh yeah, it's very useful in certain areas of research.
Prime numbers. What's prime numbers? What kind of child think? It's like a chess. Who cares what is the biggest prime number or not? But we have all the cybersecurity because of that. Absolutely. So and in a way, in this kind of dynamics of the applied mathematics and pure mathematics, in a way, and again, it's debatable what is more important. I would say that in the beginning, very much, if we go to the Babylonians and the Egyptians, I would say practical need were driving mathematics. When we go to the Greeks, yes, it was based on practical needs, but went beyond that, and that allowed mathematics to flourish. It allowed it to be the
golden age of mathematics.
Exactly. And so basically, if mathematics would only follow the technical things, it would never, probably, or very slowly would give us breakthroughs. when mathematics is leading sciences to an extent, when it develops the apparatus which nobody knows even what to do, which, like you mentioned, the imaginary numbers, people say, what the stupidity, who needs that? It doesn't exist, and it doesn't actually. And that not stupid people were saying, very, very great mathematicians were saying that, but that it's not in reality. But mathematics in a way creates reality. In a way, this is, again,
and gives us
the
tools
Bible,
to understand reality.
talking about the Bible, in the beginning of Genesis, they say, God said, let us create the man. And some commentaries says, we are creating ourselves together with God. We are co-creator. This is kind of our idea that we are created in the image of God, B'Tselem Elokim. It is not that we can, I don't know, appreciate and we can see and we have moral judgment, all that as well. But we are by definition human beings. We are creators. And mathematics is so beautiful because it's so creative.
I agree with you absolutely about it. That's why I got such a great appreciation to the Greeks, and I love reading their books, researches, written words, geometry. And that's it. I think we're going to stop here and we'll continue next time. It's fascinating. Thank you very much, Professor Misha.
Yeah, thank you very much, Tait. It was a pleasure as always.
Same.
Thank you.
Thank you.